In this video we're going to look at reversible reactions. Now first of all, by definition, a reversible reaction is a reaction that can occur in both directions. So that is forwards and backwards. Now up until now, when we've been talking about chemical reactions, we've been looking at pretty much reactions that have reactants that react and form products, and that is it. But there are a number of reactions which can go back in the other direction, where the products reform into the reactants. Now, not all reactions are reversible, but some of them are. And what's important to consider here is we are talking about chemical reactions. We are not talking about changes of state. So, for example, changes of state we know are reversible. So if I took ice, for example, so water, H2O, in the solid state as ice, you're well aware that you can melt it to form liquid water, or you could refreeze it to become ice again. So that is reversible, but it is not a reversible reaction because we don't have different chemical compounds on either side. Okay, the H2O is still H2O, so it's still the exact same chemical compound. When we're talking about reversible reactions, we are talking about reactions that again can occur in both directions, but you have different chemical compositions on both sides of the arrow. So the atoms are breaking bonds and forming new bonds to give you different compounds on the right hand side compared to the left hand side of the equation. So a reversible reaction, because it can occur in both directions, the arrow that we use looks like this. Okay, so that is the arrow we would use in the chemical equation to show that it can occur in both directions. So the first one we're going to look at is copper sulfate. Now copper sulfate, when reacted with water, will form hydrated copper sulfate. And if you take that hydrated copper sulfate and you heat it up to remove the water, it will reform back into anhydrous copper sulfate. So we have a reversible reaction. Now this copper sulfate here, the anhydrous meaning without water, is white. But the hydrated copper sulfate is blue. Now, we have made this compound before. The recrystallization required practical, where you were making copper sulfate crystals, you ended up making hydrated copper sulfate crystals, those blue crystals that we formed. Now, if we'd continued to heat it to drive off all that water, we would have ended up with white copper sulfate. So, a quick way to have a look at this reaction and to prove that it's reversible is to take a small amount of anhydrous copper sulfate, that's this white copper sulfate here, and add a few drops of water to it. And what will happen is it will turn blue because it's now becoming hydrated copper sulfate. So part 1, taking the anhydrous copper sulfate and added water to it until it turns blue, is actually this direction, this arrow going left to right. So I'm just going to label that. So that is part 1. Now part 2 suggests that you take that hydrated copper sulfate, put it in a crucible and heat it over a Bunsen burner. And what's going to happen is that's going to drive off, it's going to evaporate all of this water, leaving you with copper sulfate. So what we will see is our blue crystals would then turn white. So this reaction is now going backwards. It's going from the right hand side to the left hand side. Now it's difficult when talking about reversible reactions to get out of the habit of talking about reactants and products. everything we've spoken about up until this point has had reactants on the left hand side, products on the right hand side. But in a reversible reaction, you kind of lose the sense of which side is the reactions, which side is the products. So when we're talking about reversible reactions, it's simpler to talk about the left hand side and the right hand side. So in part 1, when we're adding water to the anhydrous copper sulfate, we are looking at the left hand side going to the right hand side. And in part 2, where we've taken the hydrated copper sulfate and heated it up to drive off the water, we are now looking at it going from the right hand side back to the left hand side, and you can see clearly it is a reversible reaction. Here we're looking at a reversible reaction involving copper sulfate. Now copper sulfate you should recognise as being the salt that was produced in the recrystallization practical, giving us these nice little blue crystals. Now the blue crystals are actually the hydrated copper sulfate, which means that in that solid crystal it contains water molecules, which is what gives it that blue colour. If we were to heat that up to drive off the water, remove the water from the crystal, then we end up with what's called anhydrous copper sulfate. So anhydrous just meaning without water. And anhydrous, or pure copper sulfate, is actually a white solid, a white powder. So what we're going to be able to do is see a very visible change. It will change from blue to white, showing that the hydrated copper sulfate has now formed anhydrous copper sulfate and water, and that water is just going to be lost through evaporation. Now this is a reversible reaction. We can see that from the double-headed arrow, meaning that this reaction can occur in both directions, forwards and backwards, which means that we can take hydrated copper sulfate, heat it up to form anhydrous copper sulfate and water, but this reaction can also occur in the opposite direction. And what we're going to see is once we've formed our white copper sulfate, if we add some water to it, it will reform this blue copper sulfate hydrated crystal. So to start with, I've got my crucible with some hydrated copper sulfate in there, and you can see that it's hydrated because of that blue colour. And we're just going to heat it under a Bunsen flame until we start to see some colour change. So already, just around the edges of those crystals, they're starting to turn white. So as the water's being driven off, so you can sort of see the steam, that's just the water that was inside these crystals being evaporated. So again, you can start to see some of the smaller pieces are turning white. Now again, this is a reversible reaction, so what we are hoping to see is once we've turned these copper sulfate crystals into anhydrous copper sulfate, so we've heated them up, all the water's evaporated, they've now become just pure copper sulfate, we should be able to add them. I've got this little beaker of water here, and we should see them return straight to that blue colour. So, there we go, you can start to see they're going mostly white now. Just heat them a little bit longer. So we've now got our white copper sulfate, so we've got anhydrous copper sulfate. I've got a beaker of water here, and when we add our white anhydrous copper sulfate, the reaction will occur in the opposite direction, and it will reform hydrated copper sulfate, which we can recognise by that blue colour. So in it goes, and you can see that it's straight away turning back into blue hydrated copper sulfate. And again, what we could then do is heat this solution until all the water evaporates again, and it will go back to being white anhydrous copper sulfate, and you could repeat this experiment in both directions because it is reversible. Now, from the video that you've just seen, we can write down our observations. So the first observation would be heating the hydrated copper sulfate turn from blue to white. And secondly, adding water to the anhydrous copper sulfate turned from white to blue. And you could repeat this process. You could then heat that up and it'd go back to being white, and then you could add water and it'd go back to being blue, and then you could heat it up again and it'd go back to being white. All you are doing is changing the direction that this reaction is occurring in, whether it's going from left to right or it's going from right to left, because it is a reversible reaction. The second reaction we're going to look at is ammonium chloride. Now, ammonium chloride, NH4Cl, is a white solid. But if you heat it up, it will break down into ammonia and hydrogen chloride. Both of these are gases. So if we take our ammonium chloride, now in the video you're going to see in a minute, it's a slightly different practical setup, but it's the same principle. So here we have our ammonium chloride, our NH4Cl, and by heating it up, it's going to break down into ammonia and hydrogen chloride. And as it gets to the top of the boiling tube, or the top of the test tube, it's going to get cooler. And what you will see is as it cools back down, it's going to reform back into ammonium chloride. So here we have ammonium chloride, white solid ammonium chloride, heating up, becoming ammonia and hydrogen chloride gas. But then when it gets cooler at the top of the test tube, or the top of the boiling tube, it's going to reform back into ammonium chloride. Now again, this isn't a change of state, because we're not just turning it into gaseous ammonium chloride, we're changing it into completely different chemical compounds. And this reaction can occur in both directions, making it a reversible reaction. Here we have a reversible reaction where ammonium chloride breaks down into ammonia and hydrogen chloride, but also ammonia and hydrogen chloride can reform into ammonium chloride. So looking at the reaction, the fact that we've used this double-headed arrow is the indicator that this is a reversible reaction. It means it can go forwards and backwards. So you could have the reaction occurring in the forwards direction, ammonium chloride breaking down into ammonia and hydrogen chloride, but it could also occur in the reverse direction, backwards, where ammonia and hydrogen chloride reform into ammonium chloride. So this is a reversible reaction, and we can cause this reaction to take place by changing the temperature. So if we heat up some ammonium chloride, it will thermally decompose into ammonia and hydrogen chloride. And if we cool down that ammonia and hydrogen chloride, it will reform into ammonium chloride. So how are we going to see those changes? Well, ammonium chloride is a white solid, but the ammonia and the hydrogen chloride are both gases. So we're going to see our white solid decompose into a gas, and then if we reverse the reaction, then those gases are going to reform back into a white solid. So the way we're going to show that is using this. So I've got a conical flask with some ammonium chloride in there. You should be able to see the white powder in the bottom of that there. And I'm going to heat it up so that you start to see it decompose into a gas. Now, we want to prove that this reaction is reversible, that it occurs in both directions. So we're going to heat it up so that it decomposes into a gas. Now you can see a little bit of sort of condensation on the side of the conical flask. If you keep watching it, you should see
that white solid breaking down into a gas. But we want to prove that the reaction is going in both directions, so we want to heat it up so it breaks down, but then we also want to cool it down so that it reforms. And the way we're going to do that is I'm going to add a boiling tube full of cold water. I'm just going to place that in the top there. So we can see the gas being formed. If you look carefully, you can see the gas being formed. It's going to start filling up this conical flask. So what's happening is the ammonium chloride that's on the bottom of the conical flask is breaking down into ammonia and hydrogen chloride. And as soon as that ammonia and hydrogen chloride comes into contact with the cold boiling tube, it's going to reverse and reform into ammonium chloride. So what we should see, if we leave it running a little while, is we should see white solid ammonium chloride form on the outside of the boiling tube. So we're going from solid ammonium chloride at the bottom of this conical flask, thermally decomposing into ammonia and hydrogen chloride, which you can see those gases swirling around in the conical flask, and then when they reach the cold boiling tube, the reaction is going to reverse, and the ammonia and the hydrogen chloride are going to reform into ammonium chloride. So when we pull this boiling tube out in a moment, we just turn off the Bunsen burner, we should see solid white ammonium chloride forming on the outside of the boiling tube. And there we have. You can see that the solid white ammonium chloride, if I just use a matchstick, should be able to scrape it off. We've got this solid white ammonium chloride that has been formed. So we have shown that this reaction is reversible because it's gone from solid ammonium chloride to ammonia and hydrogen chloride and then reformed back into ammonium chloride, and all we had to do for that change to occur was to change the temperature conditions.
So the observations of this reaction is heating the white ammonium chloride produced a white gas, and cooling the white gas produced a white solid. And again, we could repeat that reaction over and over in both directions because it's a reversible reaction. So the evaluation for these two reactions, they're examples of reversible reactions. The first one with copper sulfate involves water. Explain what is happening in this reaction. The second one with ammonium chloride involves heating. Explain what is happening in this reaction. So we'll start with number one. So the anhydrous copper sulfate forms hydrated copper sulfate when water is added. Now actually, copper sulfate, anhydrous copper sulfate, is used to test for water. If you have an unknown liquid and you're not sure if it's water or not, and you add anhydrous copper sulfate, it will turn blue, and that is a positive test for water. That's where that D came from. And when it's heated up, that hydrated copper sulfate will then reform into anhydrous copper sulfate. So when heated, the hydrated copper sulfate will reform into anhydrous copper sulfate. And for the ammonium chloride, what was happening is the solid ammonium chloride thermally decomposes because we broke it down by heating it. Into ammonia and hydrogen chloride gas, which reforms into ammonium chloride when cooled. And both of those reactions are reversible, and you can, by changing the conditions, get them to go from left to right or from right to left, and you can do that as many times as you want.